Hello everyone, my name is Abubakr Alabbasi and today I'll be presenting our paper DeepPool. DeepPool is a distributed model-free algorithm for ride-sharing using reinforcement learning. This is a joint work with my PhD advisor Vaneet Aggarwal and Arnob Ghosh. This work was done when I was at Purdue doing the PhD. Let me first introduce the problem using an example. In this slide, we have a schematic illustrating the ride sharing in a graph consisting of A-level regions A to K. There are 4 ride requests and 2 vehicles. A ride could be corresponding to 1 passenger or maybe more, as in rider 3, we have only 1 request, though 2 seats are needed. The locations of both customers and vehicles are shown in the figure. The destination of rider 1 and 4 is the Times Square, while the destination for rider 2 and rider 3 is the Central Park. The problem, the problem that arises here is how to efficiently match between the vehicles and ride requests, or alternatively matching between supply and demand. This is important to optimize for user satisfactory and for better ride-sharing services. Towards this objective, we have to answer a few questions. What are the possible scenarios to serve the passenger request? Consequently, what is the best solution among them? What about waiting time for each request, which is defined as the time from the request till the ride time of the passenger? For this small example, we show graphically 2 different possible scenarios with ride sharing, of course, because without ride sharing, we can only serve 2 requests, either this one and this one, or this one and this one, or whatever, any combinations actually, because we have only 2 vehicles. However, with ride sharing, we can serve them using only a single vehicle. Vehicle 2, let's assume that it has 5 seats, so vehicle 2 will first pick up rider 1 and then rider 2, 3, 4, and then we'll drop rider 1 and 4 in the Times Square, and then rider 2 and 3 in the Central Park. The other solution is vehicle 2 will serve, let's say, rider 1 and 4, will drop them, and then vehicle 1 will serve rider 2 and 3. As we can see, the problem becomes very hard to solve as the size of the problem, the number of vehicles and number of requests increase, and consequently the possible combinations grow exponentially. Our work, DeepPool, addresses a large-scale version of this problem in a distributed model-free fashion for large-scale dynamic fleet system. What makes this problem complex is the demand is real-time, and it is a complex problem due to the large state space, demand uncertainty, coordination in a large-scale fleet. It is very challenging to come up with real-time decision-making over uncertain future demand for thousands of drivers competing to serve the request. There is some work already exists trying to address some of these challenges to some extent. Some of them are centralized while some other are distributed. However, centralized ones require a pre-specific models for evaluation of demand, specific models for the user's authorities for waiting time and travel time. They also require a specific cost functions governing the car's total trip distance, which is difficult to estimate in practice. In addition, in a dynamic environment such as fleet management for carpooling, the trip time and the actual routes must be updated continuously based on the historical information. Hence, a model-based approach is unable to consider all of these aspects involved in the optimization problem. For further information, one can refer to 1 and 2 here. Our policy is different. Our policy is distributed, ride-sharing based, and also model-free approach. In this paper, they proposed a distributed approach for dispatching vehicles, but they did not consider ride sharing. Having defined the problem and explained the key challenges, for the rest of this talk, we proceed as follows. We'll talk about the benefits of ride sharing, followed by the proposed approach, the centralized and distributed versions of our DeepPool framework, and then the DeepPool architecture, the dataset and performance, and then we conclude. Optimizing taxi dispatch and travel times will help in reducing the passengers' waiting time and also will increase the driver's revenue. Moreover, with joint travel of two or more passengers in a single vehicle, traffic congestions will be reduced. Cost per passenger should be reduced due to the sharing among multiple passengers. Emission would be potentially reduced. The key assumptions in our work are mentioned here. We have 4 assumptions. Basically, all rides are requested with an app, vehicle state are available in real time, users are willing to share, of course. Requests are rejected if no vehicle available in a certain range, let's say 5 miles. The two figures at the bottom of this slide show the agent and the environment interaction based on the state observation, the reward, and the predicted demand. An agent an action is taken accordingly by the agent. Different from the majority of the work in this area, our approach is distributed, model-free, and discretizes the service area into small grids. Mathematically, the difference between the demand, mathematically, we define we can characterize the objective function as shown here in this slide. We have 4 objectives or 4 rewards actually. Our objective is first to minimize the difference between the demand and supply for vehicles. The second objective is to minimize the dispatch time, which is shown here in the second equation. The third objective is also to minimize the total extra travel overhead due to the detour or ride sharing, and the last one is to minimize the number of used resources or vehicles. Without going into the mathematical definition and the details, if you are interested, you can refer to the paper. However, these are the 4 components of the reward. Alternatively, we can write the expected reward in a distributed manner for each vehicle. For vehicle n at time t, the reward can be expressed as a weighted sum as shown in this formula. The action is a function of the state. The reward is a function in the state of and the action. The state is a 3-tuple capturing the system updates at time t. The first component is the or consists the current location of the vehicles, available vacant seats, the time at which passenger or more has been or will be picked up, the destinations, and so on. The second component, which is V, has the predicted number of vehicles in a capital T window. The last component, D, has the predicted demand in a capital T window. We build a simulator to train and evaluate the DeepPool framework. This figure shows the basic blocks of DeepPool. The different blocks and the communication between them are depicted in the figure. The key blocks are highlighted here in red color. The control unit is responsible for maintaining the states of all vehicles, such as the current locations, destinations, occupancy rate, and so on. These states are updated in every time step based on the dispatching and assignment decisions. Our distributed DQN policy learns the optimal dispatch actions for each vehicle. The advantage of the distributed DQN policy stems from the fact that each vehicle can take its own decision without coordinating with other vehicles. This slide shows the weekly demand trend in May 2018 for real-world data set of taxi trip records in New York City. This plot shows that the demand curves in the training and test data sets exhibit the same periodicity over a week. Similarly, the actual and the predicted demands are visually identical as we can see in this plot. In the coming 2 slides, we present some simulation results. This figure shows the number of used vehicles versus the accept rate. as compared to some competitive baselines. Clearly, DeepPool utilizes the vehicle's capacity better and thus reduces the number of active used vehicles. Also, our approach is able to serve the demand with less number of cars as compared to other approaches, thanks to polling capability and optimized dispatching policy. Here are a few baselines, competitive baselines. We consider here no ride sharing, no dispatching, while the red color here is dispatching but no ride sharing. We also observe an interesting thing here, which is dispatching of vehicle doesn't reduce much the number of used cars, especially in the region where the acceptance rate is high. Hence, our policy can reduce traffic and fuel consumption as less resources are needed per unit time. Lastly, these two figures show the mean and minimum of the vehicle utilization rate. Utilization rate is defined as the percentage of time at which a vehicle is busy serving customers. We used 6,000 vehicles in this experiment. We see that DeepPool achieves better utilization for both the mean and minimum as compared to the actual demand, which is the black dotted, the black dashed lines in both figures. This performance emphasizes that our approach learns the optimal policy for an individual vehicle, so every vehicle aims to take the best action to maximize its own reward. So DeepPool tries to fairly distribute the rewards across the different vehicles. The takeaway messages are listed in this slide. DeepPool outperforms the centralized approach due to the real-time dispatch decisions. DeepPool can take action with at most 120 milliseconds, while the centralized approaches can take up to a few seconds. DeepPool is more beneficial for drivers. It can predict best action for individual vehicles, and it is more realistic to implement in real world. DeepPool demonstrated the benefits of applying model-free distributed algorithms for ride-sharing of vehicles in a large-scale fleet. There are some extensions, interesting extensions to our work. Here in 1 and 2, our framework is extended to multi-hub ride sharing. In 3, our framework was extended to consider passengers and goods delivery. In the work here, number 4, our framework was also extended for to consider pricing and also a better matching policy is proposed. For details or for further information about this work, one can refer to this website, and also for the code, he can find it in this website. Thank you so much.